Hi, everybody. This is Dr. Nigro with the Chem Calculation screencast. This screencast is going to deal with dimensional analysis and how to use unit equalities as conversion factors for problem solving. All right, so let's start with this idea of dimensional analysis. All right, in chemistry and then later when you get to physics, you're going to find that your problems come in two types. One is an algebraic based problem. That's one where you're going to have a formula. You're going to be able to plug in your knowns and then solve for a particular unknown. Other problems are called dimensional analysis problems. All right, and these types of problems use units and conversion factors to cancel units to reach the answer. All right, so for these problems, one of the key skills is developing your plan. You're given a particular number with a unit, you're asked for an answer in a particular unit. What equalities do you know that will help you get from your initial unit to your final unit? And with those equalities, we can set up conversion factors, and then we can cancel units as we walk our way down the problem. Okay, so let's start with that idea of a unit equality. All right, some of these are known to you. I mean, some of them are going to be in the metric system, and so they may be something that you're learning right now. But others you probably know already. All right, but we can use those unit equalities to develop conversion factors. All right, so for example, all right, let's say that we know that 1 meter is equal to 100 centimeters. All right, so that is a unit equality. 1 meter equals 100 centimeters. So the meter centimeter equality, what numbers make those two units equal to each other? All right, so we can take that particular equality and we can convert that into a conversion factor. All right, and so what we do is we say 1 meter per 100 centimeters, or we can write it as 100 centimeters per 1 meter. All right, and those two conversion factors can be used to solve a problem. All right, we're going to choose which conversion factor we use based on what unit we are trying to cancel. All right, the unit in the bottom of your conversion factors is the one that you're trying to cancel. So if you have centimeters to start with, you're going to want to use the conversion factor with centimeters in that denominator so that they are going to cancel. If you're starting with meters, you're going to use the conversion factors with meters in the denominator so that they will cancel. All right, so unit equalities are one way to get to a conversion factor. All right, another way is a per statement. All right, now you actually heard me use this per statement just a second ago where I said 1 meter per 100 centimeters or 100 centimeters per 1 meter, right? But sometimes you're given a particular number with a unit that's a compound unit, all right? So let's say we're given the density of some item and we're told it's 1.65 grams per milliliter, all right? So that compound unit is a per statement. Now, per statement can be written as a unit equality. So I can rewrite this density value as 1.65 grams per 1 milliliter. All right, now you'll notice the 1 here. All right, there's no number that accompanies the milliliter in that denominator of my compound unit, so it's understood to be a 1. So that's why I can put that in my unit equality. All right, and then from there, similar to what I did above, I can write two conversion factors. 1.65 grams per 1 milliliter or 1 milliliter per 1.65 grams. Okay, and again, just like I said above, you're going to choose the conversion factor you use based on what unit you're trying to cancel. All right, so if I'm trying to cancel milliliters, I'm going to choose the conversion factor with milliliters in the denominator. If I'm trying to cancel grams, I'm going to choose the conversion factor with grams in the denominator. All right, now there are going to be quite a few measurements that we're going to come across in chemistry that are going to give us these per statements. We have to remember that the per statement, that compound unit, can be used to write a conversion factor. All right, so some of those are going to include density, as we see right here. All right, molarity is another one. All right, and molarity is moles per liter. Density is grams per milliliter. Actually, density could be a bunch of different things, but it's always something per something, mass per volume. All right, and then molar mass is another one we'll see, and that's, grams per mole. All right, so anytime you come across a measurement that is a compound unit, just keep in mind that can be stated as a per statement, which means it can be a unit equality, which means that you can write conversion factors. It will make your problem solving easier. All right, so let's talk a little bit about the plan. All right, now, this is something I like to teach my students. It's not a required piece of problem solving. It's just for me a way to organize my thoughts as I'm trying to plan what I'm going to do to solve a dimensional analysis problem. All right, so let's say, for example, that we're given, 100 grams of NaCl. All right, and I'm trying to determine how many moles of NaCl I have. So I need to convert from grams to moles. So I need a conversion factor that equates those two units, grams of NaCl and moles of NaCl. All right, well, that is going to be the molar mass of our substance with units of grams per mole. All right, so when I want to go from grams of something to moles of something, I'm going to need to utilize the molar mass. That per statement, that grams per mole, is going to let me set up my conversion factors, which will in turn let me set up my unit cancellation. All right, another example is if you're given a metric conversion. Let's say we've got kilograms and we're asked to determine centigrams. All right, now I don't have a unit equality that equates these two units. All right, we always need to go through the unprefixed unit, the gram itself, and then move back to a prefix unit. So there's no way to go directly. So instead, I'm going to convert those kilograms into grams, and then I can convert into centigrams. So this is going to be a two-step conversion. All right, but I know these unit equalities, kilograms to grams and grams to centigrams, so I can write those conversion factors. All right, your dimensional analysis problems can be one step, they can be two steps, they can be 5 steps. All right, it does not matter as long as when you are finished, the only units that are not canceled are the ones you are looking for. All right, so you should be able to check your work as you go and make sure that you are setting these up correctly. Okay? All right, so let's try a couple different problems. All right, so this first one, how many nanometers are in 264 centimeters? All right, so again, nanometers, centimeters, I don't know a direct equality between those two. All right, so I'm going to come up with my plan. So I have 264 centimeters, and I'm trying to determine nanometers. All right, so the first thing I'm going to do is go to the unprefixed unit, the meter, and then I'm going to go out to the nanometers. I'm not going to go directly. All right, so I know this is going to be a two-step conversion. All right, so what are my equalities? Well, I know that 1 meter is equal to 100 centimeters. So there's one equality that I could use to write my conversion factors. I also know that 1 meter is equal to 1 times 10 to the 9th nanometers, or a billion nanometers. And there's my other equality. So I have the equalities I need to do the conversion. All right, so now I set it up by starting with what has a number and a unit. So 264 centimeters. All right, my first conversion factor is going to go here. This unit should be in the bottom of that conversion factor so I can cancel it. And according to my plan, I'm going to the meter, and my unit equality tells me 1 meter per 100 centimeters. All right, so I check. My unit below is going to cancel my unit above, so now I'm left with the meter, right? But I'm not finished because I'm asked for the answer in nanometers. All right, now I need this meter in the bottom of my second conversion factor and nanometers in the top. And I know for my unit equality, 1 meter is 1 times 10 to the 9th nanometers. All right, I check my canceling again. These two are going to cancel. I'm left with units of nanometers, which is what the problem asked me for. All right. So now what do I do in terms of the mathematics? All right. I like to multiply across the top. So in other words, in my calculator, I'm going to say 264 times 1 times 1 times 10 to the ninth. All right. Then I'm going to divide by each number below. All right, so in other words, I'm going to take that answer from that multiplication, I'm going to divide it by 100, then I'm going to divide it by 1. But I do that in two separate steps on my calculator. You don't have to do it that way. You could multiply everything across the top and divide by everything across the bottom, and you can use parentheses to keep everything ordered. All right, but make sure you use the parentheses correctly so you don't mess up your orders of operation. All right, so if I do that, 264 times 1 times 10 to the ninth, and then I divide that by 100 and divide it by 1, I end up with 2.64 times 10 to the ninth nanometers. Okay? All right, let's try another one. This one's also a metric conversion. Kilograms is the goal, and I have micrograms. All right, so I think about those conversions. 2, 3, 5, 6, 0, 0, 0 micrograms, and I'm trying to determine the number of kilograms. All right, well, again, I don't have a conversion that will let me go directly, so I'm going to go to my unprefixed gram first, and then I'm going to go out to the kilogram. So again, this is going to be a two-step conversion. All right, so I know that 1 gram is equal to 1 times 10 to the sixth micrograms, or a million micrograms. I also know that 1 kilogram is equal to 1,000 grams. So there are my two unit equalities. I'm going to use those for my conversion factors. All right, so again, we start with the unit that has the number attached. So 2356000 micrograms. My first conversion factor is going to put micrograms in the bottom, grams up top, and according to my unit equality, 1 gram is equal to 1 times 10 to the sixth micrograms. All right, that's going to let me cancel those micrograms and leave me with the gram. All right, I move on to my second conversion factor, this time grams in the bottom, kilograms up top, and I know that 1,000 grams is equal to 1 kilogram. Again, cancellation, my grams are going to cancel. I'm now left with kilograms, which is what the answer asked for in terms of units. All right, so now I multiply 2356000 times 1, then I divide it by 1 times 10 to the sixth, and then divide again by 1,000, and I get 2.356 times 10 to the negative third kilograms as my answer. Okay? Obviously, you have to know the unit equalities for your metric system. All right, that's something you have to do on your own. Right? But once you know those unit equalities, these conversion problems are going to become easier and easier. Some of them, the one-step ones in particular, you might be able to just do in your head. All right, but just keep in mind, if you're going from a prefixed unit to a prefixed unit, you don't necessarily have a unit equality for those two values. You're going to need to go through your unprefixed base unit, whether it's a gram, a liter, time, a second, whatever. All right, just make sure you make that two-step problem. Okay? All right, let's look at this next problem. The density of a slab of granite is 2.65 grams per milliliter. What is the density of granite in kilograms per meter cubed? All right, so this is a little tricky. All right, this is a compound unit conversion. All right, so we're going from a compound unit to a compound unit. All right, so my advice, work on 1 unit at a time. All right. In other words, I'm going to look at converting grams to kilograms, and then I'll think about milliliters to meters cubed. All right. So let's think about that grams to kilograms. All right. Do I know a unit equality between those two units? Yes. I know that 1 kilogram is equal to 1,000 grams. Okay. So that one's going to be pretty straightforward. All right, the trickier one is the milliliters to meters cubed, because that doesn't seem like they should go together. But hopefully you've learned that 1 milliliter is equal to 1 centimeter cubed. So that's going to let me make the jump from the milliliter into the centimeter. All right. Now, once I'm at centimeters, I can convert into meters. Now, these are cubed units. So 1 meter cubed is not equal to 100 centimeters cubed. I need to cube that 100. And when I do that, it's 1 times 10 to the 6th centimeters cubed. All right. So be very careful. When you have these units raised to powers, you have to do the same thing to the number that is in front of the unit. All right. So not 1 meter cubed is 100 centimeters cubed. It's 1 meter cubed is 100 cubed centimeters cubed. Okay, so just be careful. All right, so with these unit equalities, now I am going to let dimensional analysis, unit cancellation, run the problem. So again, you start with the unit that has a number attached. So 2.65 grams per 1 milliliter. That's what that unit is telling us. So I'm going to start with the gram. So I'm going to put grams in the bottom. I'm trying to go to kilograms, so I'm going to put that up top. And according to my unit equality, 1 kilogram is equal to 1,000 grams. All right, so I check below, above, so those are going to cancel. And now I've got kilograms, remaining, so I've got this unit all set. All right, so I'm going to continue the problem, and now I'm going to look at my volume unit. All right, so this time milliliters is in the bottom, so I need milliliters up top. And because I can't go directly to meters cubed, I'm going to make a stop at centimeters cubed. And I know that that equality is 1 milliliter is equal to 1 centimeter cubed. All right, so I check, this is in the bottom and this is up top, so that is canceled out. But that centimeter cubed is not the unit the problem asked for, so I need to do one more step. This time centimeter cubed up top, and I'm going to meters cubed, so that's in the bottom. And I know that 1 times 10 to the 6th centimeters cubed is equal to 1 meter cubed. All right, and I check the centimeters up top, cancels the centimeters on the bottom, leaving the meter cubed. So the only units left are kilograms per meter cubed, which is what the problem asked for. So now I'm just going to multiply across the top, and then I'm going to divide by what's on the bottom, and you should get 2,650 kilograms per meter cubed as your answer. Okay, so a little more complicated, but the practice of it is the same. It's unit cancellation, so you need the unit equalities, and then you set the conversion factor so that cancellation can occur. All right, again, check. All right, cross the actual units out, circle what units remain, and make sure that you have everything in the right place. That will help you catch errors. All right. All right, now we're going to try a problem where we're going to be doing not so much a unit unit conversion, but an actual problem solved by using the dimensional analysis method. All right, so what do we have here? How many grams, so we're going to be looking for grams of NaCl, are needed to make a 1.5 liters of a 0.15 molar solution? The molar mass of NaCl is 58.45 grams per mole. All right. So, a couple things to keep in mind. This molarity can be rewritten as moles per liter. So there's another compound unit. All right. So if we have 0.15 moles per liter, all right, we can rewrite that as 0.15 moles equals 1 liter. So there's a unit equality for us. All right. The other thing to keep in mind is it wants us to get to grams by the end of the problem. But you can see there aren't any grams in any of the units that we've been given. We've got liters and moles per liter, right? And that's where our molar mass is going to come in. All right, we can rewrite that molar mass. We can say 58.45 grams per mole, and we can rewrite that per statement as a unit equality. 58.45 grams equals 1 mole, right? And that's going to let us have the ability to get to that gram that we need in the end. All right, so this is what we've been given. We've got 2 per statements, so we don't start with those. We instead start with the 1.5 liters. So we have 1.50 liters, and this is of NaCl, right? In our first conversion, we want to put the liter down in the bottom. So I go look at my per statements, and I've got that molarity, and that's what I'm going to use here. 1 liter is 0.15 moles, and this is again of NaCl. Whoops. Shuts it out. All right, so I look, the liters are going to cancel. All right, so now I have moles, but I don't want the answer in moles. I want it in grams, so I need to use the molar mass for a further conversion. All right, so moles of NaCl in the bottom of my conversion factor, grams of NaCl up top. And according to the molar mass, 1 mole of this substance has a mass of 58.45 grams. All right, so I check those units. The moles are going to cancel, and I'm going to be left with grams of NaCl, which is what the problem asked for. All right, so I've set it up correctly. Now it's just a matter of using my calculator. So I multiply across the top, divide by the bottom, and I get 13.2 grams of NaCl is going to be needed to prepare 1.5 liters of a 0.15 molar solution. All right, now, maybe at this point you didn't know what molar was. That's okay. All right, we're going to get there. But you need to recognize that sometimes these units are actually compound units, which means we can write unit equalities and we can use them in dimensional analysis. All right, now, could we have done this algebraically? Sure. All right, if we knew the formula for molarity was moles per liter, or N over V, we could have solved for N and then used the molar mass to find the grams. All right, but this is one way to do it, which is very clean and very straightforward. All right, one more. An unknown solution has a density of 0.875 grams per milliliter. If the sample has a mass of 1.25 grams, what is the volume of that solution? All right, so what do we know? We have a per statement here. We have a 0.875 grams per milliliter. All right, and so from that, we can write a unit equality. 8.75 grams equals 1 milliliter. So that's going to be useful in producing a conversion factor for us. All right. We have a mass of 1.25 grams, and we have grams in that conversion factor, and we're looking for volume, and we have volume units in that conversion factor. So we have everything we need. This is going to be a simpler problem than the one before. All right. So you start with the one that has a unit that is not part of a per statement. All right, so 1.25 grams, and we're going to set this up to put the gram in the bottom, the milliliter up top, and we know that in this particular solution, 1 milliliter of that solution contains 0.875 grams of that substance. All right, so our units of grams are going to cancel. We're going to be left with the milliliter. Do our division here, and we find that we must have 1.43 milliliters of this solution. All right, now maybe it goes on to ask you for that volume in a different unit. All right, let's say maybe it says, I don't know, microliters. And then you would need to do another unit conversion step at the end. All right, again, this is using dimensional analysis to solve for this problem. All right, we could use algebra. We know that density is mass divided by volume. All right, and in this case, we knew what density was. We knew what mass was. We could have solved that for volume. So that rearrangement would have given us volume is equal to mass divided by the density. And if you look at what we've done up here, that's exactly what we did. We took that mass number and divided it by the density value. All right, so you can do it either way. Sometimes it's easier just to use dimensional analysis. Other times, it's a quick one like this. Maybe you want to use the formula rearranged to solve for the unknown. All right, you're going to get practice with both of those in chemistry and in physics, right? But we need to be able to do the unit cancellation steps, because when we get to stoichiometry, that's all dimensional analysis. All right, so make sure that you understand how to use those per statements, how to set up the problem so that the units will cancel, and how to check your work at the end.